Welcome to a new test and teardown video. This time it's another HP. Digitizing Oscilloscope 54501A. 100 megahertz. Wow, cool. And what do you know? It's a 4-channel. And look at the quality of this one. Whoa, it's in mint condition. Nobody ever used it. I look so much forward to try this by my own hands. They got the famous, notorious one-button interface. I think HP thought this was a fantastic, good idea. However, many users reported this as the thing they hated the most. So I think I'm gonna see if it's really cool or if it's really bad. And is it really 100 megahertz? Or is this only on one channel, or what can we do? So it is from about 1988 or something like that. And it is, well, the screen is really big. Look at that. I think it was 23 centimeters. So that is 9-inch. And it's, what, 22 pounds. So that is like 10 kilos. So you can almost lift it. And in the manual, they say it fits in the trunk of your car and it's easily transportable. Yeah, definitely it is. It's made of lightweight plastics and stuff. And wow, look at that. So you can have all your probes and accessories and wires and stuff. Easy. Not gonna get lost. What have we got on the back? Let's have a look. So what is this? Electronic. This is, I think it was sent for repair? Service, yeah, okay. It was sent for service. Okay, so this is how you, okay. You take this out and rotate it. And this is wired for probe compensation. AC calibrator on the back? Really? DC calibrator output. So there's a DC voltage out. I can't wait to see what that is. Ooh, we got HPIB and display intensity on the back. So that's easy to figure out. And a very big fan. All right, let's power it up and see what kind of power consumption. What exactly is this? Some locking something that will prevent me from getting in. Well, we'll see. I don't know exactly if I'm really happy about the on-off switch being on the very back, and I don't see any kinds of switches here on the front, so that is really not user-friendly. But first of all, I will turn on mains, and there is no. And then you have, okay, it's actually in the middle at the very top. Switch. Ooh, 100 watts. Okay, so the screen is really big, but okay. Why isn't this bigger? Really? It's doing default cal loaded running. What is running? I have no clue how to use this at all. Let's just try and... No, they don't even push this. So there's... So how do I do anything? I want to select a channel. What do? I'm absolutely clueless. Aha, this is one. We hear a little diddly doot. That was not it. Okay, I need to pause the video and play a little bit because I'm just too dumb. I don't know what to... Oh, channel. Ah, okay. Channel. What do we want? 1, 2, 3, 4. 1 is on. And then what? Okay, this is different voltages per division. Millivolts. And a lot of volts. Okay. Okay, so far so good. Bandwidth limit. Okay, here we go. We don't want any bandwidth. And it's DC. Probe is in 1. We can even say some... What is that? More? More probe. So that's it. So this is channel 1. But how do you move it up and down? Let's see that channel. Wave... Yeah, I don't know. I don't know. I'm clueless. I'm totally clueless because this scope is not like any other scope. They did what they can, what they really could to morph everything into their own funky interface, and that means you are completely lost. Time base. Okay, let's try time base. Okay, aha. Now we're in time base. Then yada yada yada. Okay, that is good. 500 microseconds. Okay, goody. Reference. Okay. Ooh, that was sexy. No, we don't want that. So that was time-based waveform. Ooh, what is that? What is that? Waveform mesh memory. We got display. Okay, it's pretty cool. Channel sensitivity. Blah, blah, blah. Offset. No. How do I change the channel up and down? So this is the volts. Ah, here we go. This is the offset. And we can go. Isn't that a little bit odd? So that this is in the middle when this is 0. What? How is that? So this is your 0. No way. That is definitely not okay. 1 volt per division. 500. Okay, there's a total crappity crap when it comes to different voltages, then it just jump up and down. So, ooh, we need to do some calibration. But I think that was in utilities, self-test, test all. Let's run the self-test and see. Okay. Ooh, yes. What else is gonna blow up? So that's it. So now everything is fantastic. That's really good. And we're... No. Probe cal. Self cal. Service menu. Ooh. We can do a lot of funky things here. And the screen is really nice and sharp and easy to read. Oh. It was from... This is 90. So the software is from 90. Cool. Self probe cal. Start cal. What do I do? Oh, I need to connect it to the rear panel. Alright, I'm gonna play a lot with this, and I think I'm gonna come back and look like I know something. I'm playing a little bit more with channel 1 and channel 2 connected. I can just enable some more channels, so that was easy. It's a little bit weird with the channel set up here with voltage per division and stuff like that. I'm a little bit unsure if this is correct, but I didn't calibrate channel 2. I only calibrated channel 1 by connecting the BNC to the back, and that is of course needed for this thing to go accurate. And the auto scale feature also seems to be working quite well. We get a picture on. Then I found display. And then you can do average, envelope, number of screens. So you're gonna have, oh, so you can put the different channels on different screens like this. See, that is really sexy. Or you can have them both on one screen, or 2 channels here and 2 channels there. That's pretty cool. Access frame. See, this is also Very nice. You can have everything on, or connecting dots. Aha, that is better. Right, this is more normal. But it also seems like it affected, yes, it did affect the update rate. Oh my gosh, something happened with the update rate. It's now, I don't know if you can see this, but when I'm connecting or disconnecting a channel, it takes a second to update it, but when I see, it's instant. So this connecting dots is a feature that will take a lot of CPU time to actually do. Whoa, now the screen is super slow, so that we can't really use. I also found out about the blue text here. That's actually all the measurements, and this is super cool. Look at that. You select a standard measurement. It could be frequency, and then frequency channel what? Okay, channel 1. And then we get the channel for, or the readout for channel 1. But see, if we do it again, frequency and then channel what? Okay, we want channel 2. Bada bing, bada bum. And then it reads out everything here. It's really nice. So that is super easy to use, and you can just continue to add measurements, and then we'll just scroll up. You can have 3, let's say voltage peak, channel 1, and then it goes on like that. So that is super easy to use. But when it comes to the channels and the voltage or time and stuff like that, then it's, I don't know exactly if I like this. It is a little bit funny. Fine. What is fine? Okay, time base. So that was the time base, and then you just scroll around here. See? So now we're not using connecting dots, and then we go faster, and then it actually does connect the dots somehow. So there's some funny stuff it's doing in the different time base settings, and it's seems to be working quite alright when it comes to that. So that was great. Then channel again. It's a little bit weird with this millivolt per division here. It's easier just to click on it and then say 1 volt, and then it goes, and this offset, and then you can dial it. I don't understand why it's not 0 when it's in the middle. So that is a little bit weird. If we go to channel 2, let's try something else. See, for channel 2, the offset seems to be correct. Aha, so it's probably something about the calibrations and stuff. Alright, so that is probably something we could easily fix. Now what I want to do is test the maximum frequency in one channel mode. And let's see what kind of speed there is in this scope, because they claim 100 megahertz. Okay, I think I figured this out. See, now I'm in the time base, and look at all the dots. So there are just a number of dots this thing will do. So see what happens when I just dial around the time base. See what happens with the picture. The dots gets closer and closer, because now we have much less dots. So that is the trick. You're not supposed to have a picture like this, right? It's supposed to look like this, and then it's perfectly fine. So this is 1 kilohertz, but then I go to channel, and look at the millivolts per division. If I click this and dial, it's just jumping in those funny voltages per step. That is a little bit annoying. And the same comes with the offset. It's also some really funny. I'm not too happy about that. So that is the weirdo thingy. Okay, well. So anyway, now we're gonna go and speed up a little bit. I just discovered something funny. So this is now a 100 kilohertz signal. When I put in 1 kilohertz, I adjusted my signal generator, so I had exactly the right full 100%. And then I just dialed the time base, and now it wasn't in the center. So So I had to go into the channel and adjust for the offset to get the picture back. Just a little bit, but still quite funny. But the level is still exactly the same, so that is pretty good. So now we are in 100 kilohertz, and let's gotta go to 1 megahertz, right? And then just get up here. Oh, see what I'm saying? Now it's actually touching the top, so that is 1 megahertz. Let's try and get 10 megahertz, and then again. Ooh, can you see now it's doing this funny thing? Let's try something funny. Single, and then clear the display, and then single. So this is a single sweep of 10 megahertz, and you get 2 dots. Single, 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 single. So every time I hit single, I get a new sweep, and you get only 2 dots. So how many megahertz is this scope really? Can you see how many samples it takes? Now we run it again. This is only 10 megahertz. My gosh. So if you're doing single, it's absolutely useless for anything. Let's go down to 1 megahertz again and see if this is gone in. Okay, here we got a nice picture. We go single and we clear the screen. Single, and what? Look at that! We just got like 20 dots. So this is a 1 megahertz signal. Oh my god. So maybe this got a bandwidth of 100 megahertz, but its sampling rate is just so incredible low. Really? It's in the kilohertz, the rate of sampling, because you see, clear display, single shot. Oops, and again. Let me do it again. So this is 1 megahertz. Okay, let's go down to 100 kilohertz, and then single. You see, we got all those dots. Oh, we actually see the time. So this is 1 microsecond per division. Then you got 500 nanoseconds per sample. Really? So this is not one microsecond is 1 megahertz, right? So it's 2 mega samples. This is what this scope is doing. That is how it is. Single. And then we run again. And then we go down to time base. And we go to channel, offset. Put the screen back here. Fantastic. Single, clear screen, single. That's the dots. Your 500 nanosecond per dot. That is how it is. This is 100 kilohertz. So it's really nice and useful for 100 kilohertz. You can see the curve, and I think if we go to display, we should be able to connect the dots. Ta-da! And it's a nice sine wave. Aha! Now I got a good idea. Let's try and up this again. So that was 100 kilohertz. So let's say 1 megahertz, and then we go. Now we are in connect the dots. Run, and we time base. So we get like, yeah, okay, like that. Okay, single. Clear the display. Single. Haha. This is your connect the dots. All right, so this is 1 megahertz. How cool is that? Yeah, and you see 500 nanosecond per division, and we got 1 dot per division. Let me do it again, single again, and now it adds the dots in between again and again and again and again and again, and now we have a nice sine wave. All right, so this is how it works. I think that is pretty good. It reveals about the sampling rate and all that kind of stuff. Maybe we should try and give it a 100 megahertz signal and see what happens. Yeah, that is what we need to do. Here we go. This is your 100 megahertz signal. Let's try and go to measure frequency, channel 1. Yep. Here's your 100 megahertz signal. It's actually reading it quite alright. Let's display, connect the dots is off. And then a DVD like that. Fantastic persistence. You can even add some address or some envelope. I mean, yeah, you definitely need to connect some dots. And let's go single, clear display, single. No, single. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No lock. So that means in really fast mode, this is of course the fastest. 2 nanosecond per division. This is definitely the fastest it can do. There is no single. Nothing works in single. It's because it works. You have 10 nanoseconds per division, and there is 500 nanoseconds per sample. This is how fast the sampling system can run. So what you see here is a time interleave from the sample. So the trigger system is really, really fast and good. And the jitter you see here, that is actually the timing accuracy of its re-triggering. Yeah, definitely how it works. I think it's enough playing around with this stuff. I think we should try one more thing before we open it up. And I really wanted to try and input 4 channels at the same time. Alright, 4 channel modes works, and this is 1 kilohertz and 3 kilohertz input. I see a little bit of jitter, so the trigger is actually affected a little bit by adding more channels. It becomes a little bit of jittery time-wise. And it happens actually already in 2 channel modes. See, channel 1 is super duper nice and accurate now. So, and this is again because the scope is when it's triggering. The next 500 nanoseconds is when it scans all the sweeps and stuff. So there is some accuracy in the reset of the 500 nanosecond timing, right? So that is of course how you see the jitter, I guess. But it actually worked with all 4 channels, and so that is quite good. I didn't really try all the different save and math measurements, utilities and whatnot. You can do a million things with markers, and there's actually a lot of stuff, and it's not that difficult to figure out. And I must say, I'm not a big fan of this knob thingy, but it's not at all a big problem. I'm not going to call it a huge problem, because all you have to do is click time base, dial this, yada yada yada, and then it actually responds quite fast to user interfacing, channels, easy to use. Again, you get used to this really, really fast, and it's not a big deal. It's not like any other scope, but it's not supposed to be like any other scope. So yeah, I'm not gonna call this bad in any way, because it's actually quite sexy. But it's not fast or anything, but for audio or, you know, debugging slow stuff, it's pretty good. That was super easy. Just take off the screws around the edge here and lift up the top. So that is a power supply unit on the top. And what do I see? Some easy unlocking. What the heck is that? What is this? A little pokey thingy. And there's another one right here. What is the idea? Ah, this is so you can. Wow, that is sexy. So you unslide the power supply like that, and just one connector here, and then this is the power connector. That is super brilliant, guys. And what do I see here? This is a 68,000 and 2 EEPROMs, of course, because it's a 16-bit data interface. Wow, a lot of good old components. And also what I see here is 998. exactly the date and everything. So now we know exactly how old this is. We got a crystal down here. This is the usual display interface. So that's just the CRT. Everything related to the CRT is just that board. Single layer board. Just a television set, more or less, right? But I need to pull out the power supply and see what's in there. Is it really that easy? Ha! Whoa, that connector is just too easy almost. Bada bing, bada boom. That will be all the channels. Some capacitors, some trimmers, some flat cape. Oh yeah, okay. This is the front panel. Buttons that goes to some of the I/O chips. There will be some processor support chips around here for interfacing, analog and digital inputs and stuff. And we got some, maybe there's some custom funny chips, because this one is a no-name BGA or some stuffy running at 40 megahertz. And what else is that? 50 megahertz. So this is probably how it makes everything. Tons of little analog. And this will be the AD converter, I guess. Yeah, maybe this is just memory interface. Yes, this looks exactly like memory chips. Yep. And some other stuff around that. Oh, we got some more funky chips down there with some software in them. I can't really make up what that is. Microcontroller from Intel. Maybe we can have more of a view what's going on. Maybe we can take out this board. Oh, I got to be the most crazy, because look what I found. Of course they got this. But look, the entire case is made in one unit. It's not assembled in any way. So this whole plastic piece is cast in one piece. How the heck did they do that? It looks like this case is also supporting multiple modules or slide-in things, not only the power supply. Maybe they're using this case for other instruments as well, because yeah, why not? We've seen this a lot of times before with HP units. Just plug in different front back panels, so you're probably gonna find exactly this case reused. But I really like this, the way that this was mounted. So I took out the CRT board. Got some memory chips, a little sounder. Ooh. This is the SRAM with a battery inside. That can be a problem to replace because it's soldered into the PCB. Ooh. Luckily, it passes everything, but I think there is a possibility to measure the voltage somehow, right? So we could see 19.66 megahertz, little programmable chip, and the brain, the 68,000, yeah, and the software. Pretty funny, it's two different chips. Isn't that funny? So this is the high and low part of the software, and it's just using completely different type numbers. That is funny, isn't it? Yeah, but that is more or less how the main board looks. I'm not going to pull out the main board because that is just too big a hassle. So this is the CRT module. Everything here is nice and clean. Oh, look at the cooling for this diode. And that will be the flyback power transistor for the high voltage. We got some high voltage parts. They protect it really good. This is a beautiful CRT design. I really like it, and this is why you don't see any dark spots, any dark brown burned components or anything. They just know what they're doing. So this is really, really good designed. Maybe we should try and open the power supply as well and see what they got of cool goody things. Oopie doopie, that is some heavy juice. So this is doing 100 watts. Ooh, this is computer products. Yeah, and this is also what I heard. This is not made by HP, right? This was a product they bought for this. Component type custom rectifier. Ooh, funky. So 98. Hong Kong, yeah? So how are we gonna open this one? Let's just pull out all the screws and see if it falls apart, right? See? There's a HP part number. Service, yeah. That power supply is just full of screws. Different types of screws as well. All those screws just for the power supply. And it's because a lot of stuff is cooled by the top or is using the top for stability or for shielding. Wow, it's really a complex unit. A little. Okay, so there will be some power transistors, and there it's used for a shield and cooling at the same time. This is where all the regulation and all the brainy things they will be located, right? Because we don't find any other funky ICs and stuff. Got some linear regulators and some power switchings and stuff. But I really don't like the way that you are cooling down diodes on metal shields directly up your capacitors like this. Okay, this unit is mounted directly in the front of the fan. So all this air blows straight through this unit. And that's the only way they can get away with this kind of design. Because, of course, you don't want to warm up your capacitors. But, of course, the fan is just blowing ice cold air straight through. So when it comes to electrical, of course you want this to be as close as possible, because this is better for EMC and for noise and everything. You can even see how the circuit is, right? Got the AC here, and then we got DC there and DC there. But yeah. So this is what they're doing. See, heat sinks, straight up capacitors, all over the place. And they're not using diodes meant to be heat sinked. They're using normal diodes like that, and then cooling them down. That is a little bit funny. But other than that, mains input was here, right? Mains fuse, mains input. And look at that. Philips capacitor. No, we don't see this reefer shit that we always see. That just cracks and destroys everything that is good. So luckily we don't find reefer components in here. So that's Philips, and they're just good. Ha! I am so happy about that. So this will be the common mode chokes. That will be the rectifier. Do not touch this one. So no, I'm not going to touch that one. T41, so that's some transistors and stuff. Yeah, flyback. That's what it is. One transistor primary flyback converter, but it's only 100 watts, so of course, yeah, we can do that. And then just some diodes and filters and stuff and everything else. Really, really nice power supply. It's quite big and heavy. That'll be a relay or an optical, right? Yeah. Now I just need to assemble this beauty. So now this thing is assembled, and as always, if you can't find age indication on equipment, always look on the CRT. See again, 89. So that is just a classical way to date old electronics. Thank you very much for watching. Stay tuned for more.